Hello everyone, good morning. So today we are here from GE Aerospace to talk about how we are solving some of our fundamental problem of huge volume data management using DynamoDB. So myself, Balamurgan Krishnamurthy, one of the software architect in GE Aerospace. I also have Shweta Ravankar with me. She's our technical product manager. And also we have Jibril, who's our data engineer. So this is our agenda. So first we walk through GE Aerospace as a company, like what we are doing, and then like what is our business problem, and then like what solution approach we took to solve the problem, and some of the key takeaways and the path forward, and followed by Q&A. So this is our plan for today. So with this I'll give it to Shweta to present like our GE Aerospace as a company. What is Shweta?
Thank you, Bala. Hi, everyone. I'm Shweta. I'm the technical product manager working for GE Aerospace. Before we get into how we solve the voluminous the challenges that we had, I quickly want to introduce you all to the GE Aerospace, which is a leading aerospace company, and with safety, quality, delivery, and cost being our primary focus. GE Aerospace continues to lead designing and manufacturing aircraft engines that power military, commercial, and the business jet engines worldwide. The fact that every 2 seconds, GE engines fly and take off and fly down, or around 6 lakhs of people, travel at any movement powered by aircrafts powered by GE engines itself is a testimony that our GE engines are so reliable and safe to travel. So safety being our top priority, it is very critical for GE Aerospace as a business to maintain that trust and excellence in this aerospace industry. Having said that, in addition to the manufacturing various engine portfolios, GE also has a commercial services department which provides comprehensive services to our customer that help them to manage and maintain the aircraft engines and operate them efficiently. What we do here is we provide extensive support for our customers to manage their maintenance cost, low downtime, and also ensure that the engines are operated with safety and efficiency. Customers typically benefit from the expertise that we have in GE Aerospace and the GE Aerospace resources, ensuring that the engines are maintained with the highest standards. Having said that, as we all know that aviation industry is seeing a remarkable growth, and we predict that over next 5 years there will be a huge demand in customers, asking for commercial engines. This expansion itself is a great representation for a business growth opportunity for us as a GE business, and at the same time, it comes up with a lot of challenges. With increase in the volume of customer demand, there is an increase in the contracts that we have to handle. And with the increase in the contract, we also see there is a lot of volume that comes along with it. And for us as a GE company to be competitive in the market, it's very important that we design our systems that help our businesses to respond back to the GE customer, to all our customers with fast and more accurate data. But at the same time, as a company, we also want to make sure that our digital solutions that we are providing to handle this volume is cost effective. So, having said this, I'll pass on to Bala, who will take you all through the journey of how did we build a solution which is more cost effective and able to handle the volume that we will see in the next upcoming years. Over to you, Bala.
Sure. Thank you, Shweta. So to solve some of our volume data problem, a typical existing architecture look like this only. Okay. Typically, there will be a user interface where user feeding the input, and also it collects information from like multiple other sources. And then like there will be a business logic in place where using our proprietary algorithms, it will run and the data is getting generated. And the typical data goes to an RDBMS system where typically we primarily use Oracle, where it stores the information over there. From there, the consuming application, like downstream applications, will read the data, and then the reports are getting generated. And based on this, some business decisions are made. Okay. And then like the data backups, right? Because continuously the data is getting generated and we store the data in Oracle. So we need to take the backups, right? For multiple reasons like audit purposes, things like that. So this is how the existing architecture look like. In this architecture, there are some problems. Okay, this is where the main problem is this architecture is not able to meet our latency requirements. As the business problem stated, our industry is growing, right? That means more data is generated, and now customer demands the data needs to be processed much quicker and decision to be made like much quicker. So we have like very stringent latency requirements for the volume. And also like they wanted to get scaled because our business is growing. So today, like it's growing like 5 times more, right? Starting like next year, the volume will become 5 times. So the architecture, like what we need to develop, should be scalable. So this architecture, what you see here, is not scalable. And also like a lot of touch points here, like manually things are managed. For example, the data backups today, and support engineer log into an Oracle or log into like a downstream systems where they take the backup and they put into like some storage kind of thing. Okay. And also it's having a high fixed cost. So though the system is used or not used, we pay like a very high fixed cost. So these are some of the challenges we face. And this is where we started evaluating like multiple options with help of AWS. Okay. Especially the way we store the data. So here we use Oracle as in storage. We thought like for volume, we reviewed this and make sure like we do the right thing. And that's why we started evaluating like DynamoDB as our technology for storing the data. Some of the design considerations we have listed here, and also like some of the trade-offs we made while choosing the DynamoDB. Definitely like one or critical use cases to handle the data volume where the system should handle like 5 times more data than like what it is having today. And also we evaluated like the patterns, like what pattern we are going to query the data, right? And for our use case, it's going to be like a query all pattern, like whatever the data generated, we usually like query like every data. And then we want to make this process as synchronous as possible, right? That means we want to like separate the data creation and data storage into two things, right? Data's creation should not dependent on like data storage. We want to like make it like as synchronous as possible. And also we want to make sure like we want like make the system to be flexible so that like the business logics can be incorporated easily at any point of time. And the primary use case is like to take care of the latency. We want to make the business logic run parallelly so that like it takes care of the latency requirements. And there are like some of the trade-offs we made, right? As technology choice, we consider DynamoDB. We understand there are some trade-offs we need to make. One, the data retention, right? We should be like very careful on like how long we are going to store the data into DynamoDB, right? And then the custom SQL. So today Oracle or RDBMS technology, it's evolved so much. There are like multiple queries you can write. It's fully flexible to query the data like whatever you want. But here, as DynamoDB as a technology, we need to evaluate how much customizable you want for your queries. And then the predetermined usage pattern, right? Once the data is stored in DynamoDB, what are the patterns you want to query? So these are the considerations we made and trade-offs we made. So based on this, we come up with our first architecture for the volume data management and including the DynamoDB. So this is how the approach looked like. This is our iteration 1, where we created the user interface, and then we started parallelizing the transaction, like serial processing and parallel processing. We made the business logic in such a way that the transaction can run parallelly. And then like it continuously load the data into DynamoDB. So DynamoDB is a technology where storage technology where It's capable of like storing like the data, what we are generating, the speed in which we are generating. And then the data goes to Lambda, right? Lambda reads the data, and then it generates a report where the reports are stored into S3. And from there, the downstream applications are consumed and the business decisions are made. So here we solved a number of problems. For example, one of the primary problem what we solved is like a parallel processing, right? Because now the system can able to generate the data like much quicker, much faster, and DynamoDB as a technology is capable of storing the data in the speed we are generating. And definitely the traceability, like AWS has a tech stack, right? At every layer, you can easily track, like trace a track using the CloudWatch, things like that. We have not done like anything specific, but service by default providing all these features. With this, we can also meet the latency requirement, whereas things are like parallelly we can do. It's exactly meeting the latency requirement. At the same time, like this architecture created some problems, right? One, the cost, right? So now the business logics are creating like so much of data. We put the DynamoDB capacity to accommodate the data. That means our cost is increased, right? Earlier we pay like 1 time. Now we started paying like 5 times more. And then like it's not able to scale that much also, because the moment more data is there, I need to rise capacity like so much that we don't want to do that, right? We want to meet somewhere middle where data generation is possible. At the same time, like DynamoDB also should be capable of taking the load. And still this process is like synchronous. For example, the data is getting generated in the business logic. And once it is done, the data goes to DynamoDB, right? And then goes to Lambda. Again, another data getting generated. So it's became like so synchronous. We have not made it as synchronous. Then we realized this needs to be optimized to meet our business requirement. So that's why we started with optimization. So Jibril, who's our data engineer, will help us like what optimizations we made on top of this to make our architecture final. So Jibril, over to you.
Thank you, Bala. Hello, everyone. My name is Jibril Abdullah. I'm a senior data engineer at GE. Bala mentioned 3 problems in our architecture: low performance, high cost, and synchronous processes. I'll explain how we fix them. So the output generated by our application consists of numerous CSV files. This data, which can be tens of GBs in a day, must be consolidated in a database before reports can be generated. So the sheer amount of data required a data store capable of providing millisecond latency at any scale. And for this reason, we chose DynamoDB. Initially, we approached the design with a very SQL-oriented mindset. This meant that storing data in a way that resembled a typical SQL table. So where each row of a CSV file is a row in DynamoDB, is an item in DynamoDB. So consequently, writing and reading each item required a separate call to DynamoDB. With millions of items, this approach resulted in performance issues. Due to the sheer number of calls, there were millions of items, so we had to hit the DynamoDB server millions of times. To address this, we observed that while the number of items generated by was in millions, each item was relatively small. It was just 400 bytes. In some cases, it was even less than that. Given that DynamoDB maximum allowed limit for an item is 400 KB, we saw an opportunity over there. We combined 1,000 data items into a single data item. This is what we called sharding. So we divided our entire data into multiple shards, each of size 1,000. And then in one call, we could write 1,000 items to DynamoDB and read it. This consolidation reduced 1 million items to just 1,000 items, resulting in 99.9% reduction in number of DB transactions. It also resulted in 95% performance improvement. Although this solution improved our performance, it was still pretty costly. To further optimize costs, we compressed each DynamoDB item, which already contained 1,000 data items before insertion. So on average, this compression resulted in 80% reduction in item size. So 1 MB item could now be just 200 KB. So with this 80% reduction in item size allows us to fit 80% more data items into a single DynamoDB item. Thus, 1 million DynamoDB items with sharding were reduced to 1,000, and now with compression, 1,000 items became just 200. This 80% reduction in data volume translated directly in 80% reduction in data volume and storage costs, data storage costs and transfer costs. Additionally, there were 15% improvement in performance due to reduced number of high latency network calls. With this, the performance and costs were optimized. The next challenge was to make this synchronous process asynchronous, as well as to handle huge data spikes. Next slide, please. So at any moment, there might not be any data generated, but the next moment, hundreds of MBs of data might be generated. This is what we call a data spike. So for that, we introduced Kinesis Stream as a middleware. So for that reason, we introduced Kinesis Stream as a middleware between our data producer and DynamoDB. Kinesis Streams can handle massive amounts of data, scaling automatically to match the data throughput. I hope I'm clear. I just got a notification that you might not be able to hear me. Okay, I'll continue. So Kinesis Streams can handle massive amounts of data, scaling automatically to match the data throughput. Technically, DynamoDB can do the same, but handling spikes in DynamoDB would be a lot costlier, as you would have to allocate large WCUs and RCUs. Kinesis can do the same with a fraction of a cost. This allowed us to manage our costs as well as decouple data producer and DynamoDB, thus making it asynchronous. Both the components could now scale independently, reducing bottlenecks and throttling. So coming to the new architecture, the business logics now perform data compression, and data was pushed to Kinesis streams. From there, the data flow control will take the data from the streams and insert it into DynamoDB. Once the data is inserted, Lambda functions are triggered, which take the data from DynamoDB, perform decompression, and write the reports. Now I'd like to invite Bala to reflect on the key takeaways. Thank you.
Sure. Thank you, Bill. I think the development is not like finished. Our architecture is still evolving, right? At this point of time, our business is like so demanding, right? We try to solve like one problem at a time. I believe at this point of time is solved enough so that like our customers started accommodating the system. So here are like some of the key takeaways when we deployed the solution. While using the DynamoDB, we need to understand the data consumption pattern very clearly, right? Like after the storage into DynamoDB, how we are going to query the data, right? What are the use cases after you keep the data into DynamoDB? And second, we need to take all the stakeholders along with the solutioning, because RDBMS as a technology has evolved so much. Your business might be directly using the RDBMS, and your upstream and downstream might also using the RDBMS in so different ways. But now, as we are changing our storage technology, it's very important to make sure we take all the stakeholders, including our business, upstream, downstream, along with the solutioning. And refer API documentation line by line, because we started like introducing like from RDBMS, we started introducing the new technology like Kinesis and DynamoDB. It's very important to understand like how the technology built. On high level, you might know, but everything lies on the details. The documentations are so clear where after reading it, it's very easy for us to do the implementation. And definitely the partnership with the AWS team, the solution architects and the engineers, where we had like a very frequent reviews to make sure we are doing the right things in an optimized way. And this helped achieving the solution needed by the business. Now our business started using the solution, and we are evolving from here. I think that's all we have. We now back to the AWS team for any Q&A. Thanks again, everyone, for listening us. That's all we have.
Yeah, thank you so much. So we have few questions from the audience. So one is from Manuj. He's asking any latency or any other performance issues in query outputs when you reduce the volume to 80%?
So we were expecting some latency, some increased time, but we actually got a better performance from that. Since we reduced the number of calls from say 1,000 to just 200, there was an improvement over there, and overall we saw 15% performance improvement and no downsides to that compression.
Thank you. So another question from Somik. So now we have Aurora DSQL, which has been unveiled in reInvent. Is your team exploring Aurora DSQL in place of DynamoDB, considering that it's essentially allow for low latency SQL structured data queries?
Yeah, very great question. So we also learned during the reInvent. Definitely, as I said, like we are not finished with the complete architecture, still evolving, right? Our business is like so demanding, right? They want like latency should be like as quick as possible. Definitely, there's an opportunity for us to explore, to figure out like how we can use the dynamic SQL and see how it can solve over some of our problems. Yeah, we are considering that.